Imagine a massive influx of traffic hits a website and the system slows to a crawl. To fix it, you must go deep inside. A web server is essentially a high-stress digital restaurant kitchen. Orders fly in, meals have to go out, and every single part of the staff needs to know exactly what to do. Linux organizes this kitchen into distinct layers. At the very bottom is the physical hardware, your ovens, prep tables, and refrigerators. Right above that sits the kernel. You can think of the kernel as the head chef, deciding exactly how much power and space each task gets. On top of the kernel, we have the applications. These are your line cooks, actively putting the meals together. But you, the user, don't talk directly to the chef or the cooks. You speak to the waiter, a text-based interface called the shell. You hand the shell your order, and it translates that request for the kernel. To manage this restaurant effectively, you have to learn how to communicate through that waiter. It's the primary way you'll reach the kitchen staff to see what's actually happening inside. This diagram shows how Linux organizes all of its ingredients. It uses a strict upside-down tree structure, starting from a single point called the root directory, represented by a /. Every specific function has an assigned room. The /home directory is the staff locker room, containing user files. /etc. holds all the configuration files, essentially the restaurant's recipe book. And /var is where the system keeps its logs, recording everything that happens during a shift. Looking closely at the file permissions section, we see how Linux secures these rooms. It uses a simple tag system: read, write, and execute. This ensures the dishwasher can't accidentally rewrite the dessert menu. Commands like chmod and chown let you assign specific color-coded keycards. You can grant access to individual users or whole groups of staff members at once. When you need new tools, you don't build them from scratch. You call a delivery service. In Linux, this is called package management. This section illustrates the two most common delivery fleets. If you're running a Debian or Ubuntu system, you use a tool called apt. For Red Hat or CentOS, you use YUM. You type one command, and the delivery truck fetches your new software, like the tools needed to run a website, and sets everything up automatically. Memorizing this strict layout and permission system means you always know where your tools are, and you never accidentally leave the back door open to unauthorized guests. Suddenly, the midday rush hits. The website starts timing out, your server is overloading, and you need to intervene from miles away. This panel breaks down SSH, or Secure Shell. It acts as an encrypted walkie-talkie. By exchanging secure keys, your laptop connects directly to the server's command line, giving you immediate control. Moving to the disk and memory management panel, we start our diagnosis. First, we type df-h to check the physical storage. We need to know if the hard drive is completely full, which is like running out of space in the pantry. Next, we run free. This checks our RAM, the system's active memory. If the RAM is maxed out, it means the cooks have completely run out of counter space to prepare orders. You always run these two commands first. Before you try to fix a crashed server, you have to prove whether your bottleneck is the storage drive or the active memory. If the memory is completely full, one specific application is usually hogging all the resources. We need to hunt it down. This window visualizes the process management system. By typing top or PS, Linux gives you a live scoreboard of every running application. Each one is assigned a unique process ID, or PID. Once you spot the process hogging all the kitchen's burners, or what the computer calls the CPU, you type kill-9 followed by its ID number. This forcefully stops the rogue program and cools the system down instantly. The immediate crisis is over, but we still need to know why the crash happened. By reading the text files in the /var/wog directory, we can retrace the application's exact steps leading up to the failure. Looking at the networking tools diagram, we verify the fix. We use netstat to confirm our web server port is officially open again, and curl to send a test request to our local address. These monitoring and termination commands take the guesswork out of a crash. You go from wondering what went wrong to seeing the facts and removing the problem with precision. Typing these commands by hand works for one server, but if you manage 50 servers, manual troubleshooting is impossible. You need to write automated prep recipes. This graphic maps out shell scripting. It starts with variables, storage containers for dynamic data, like server IP addresses. Next, conditions use if-then statements, giving the script decision-making power. Finally, loops tell the script to execute instructions across dozens of machines automatically. Shell scripting turns a single administrator into an entire automated IT department. Tasks taking 3 hours of manual clicking can run in a matter of seconds. You can write a single script that bundles your website files together, logs into a remote server, and sets up the newest version of your app for you. Focusing on the logging timeline, we see a crucial final step. A good script always writes down exactly what it did. Appending outputs to a log file means a human administrator can review the exact history later. Combine a solid file hierarchy, sharp permission controls, and automated shell scripts, you build an infrastructure that actively manages itself. This cheat sheet displays the massive library of tools available to you, from organizing the physical disk to tracking network connections to writing complex control flow pipelines. Linux is the backstage machinery powering the modern internet. It might look intimidating from the outside, but it is built on simple, logical rules. All you need is a terminal window and the curiosity to start typing.